So it's time to start a pretty long handout with a lot of significant material in it about the precise definition of a distribution. And we're not just going to lay out the definition and then take consequences of it, because that's not what I want to do here. What we're going to see is, by analyzing what we've got so far and being careful about what we don't have so far, we're going to see that we really do need extra conditions on distributions. And we're going to approach it in a few incomplete steps and then finally get the complete answer by the end of the handout. So the situation, as you know, is we've been focusing on solving a linear differential equation, linear inhomogeneous differential equation. This is some linear differential operator with constant coefficients. You can think of it as mass spring, for example. Here's the solution we'd like to find, and here's the forcing on the right-hand side. And Duhamel's principle has said that there's a beautiful solution to that. Just take a fundamental solution, in other words, a solution to the hammer blow, which will in general maybe be a distribution, might be an honest function, we're not sure. This is certainly a distribution. So this we totally needed to get into the language of distributions. We're not sure if this has to be a distribution in general cases. It actually isn't in the case of the mass spring, but as far as we know, in general, it's going to be a distribution. And then we've got a definition of distribution convolved with a function that will give a solution. Okay, but the problem is that we don't know in general whether this is going to be a function or a distribution. And maybe more disturbingly even, is for general distributions, we don't have any good idea of what those really look like. So far, our definition of a distribution is just something that takes a test function, there's the space of test functions, and gives a number, and we've had good reason to require it to be linear, and we're going to use that throughout. But otherwise, we haven't made any further restrictions on it, and that's an extremely formal kind of gadget, okay? And ideally, I don't know if it's an absolute requirement, certainly in this case, if someone poses this kind of question for you, where this is about just ordinary derivatives, this is an ordinary function, and they say solve this, it's pretty irresponsible to create some absolutely completely new formal gadget that doesn't have any clear relation to the old gadgets like functions and say that you've solved the problem. Now, in the mass spring case, this guy is nice enough. The solution of to the hammer blow is nice enough so that we can be pretty confident that this is okay. But it's really hard to see how we could say anything in general. And so what we're going to need to do is put on an additional condition on what a general distribution does so that we know that this actually makes sense in more generality. So, as I would say in the handout, a good example of what we don't know yet is if you take like a test function phi, and it looks like this maybe, and then you just shift it over a tiny bit. And we have a notation for that. Oh, I think I forgot to use the parentheses in the handout. Maybe I'll edit it. Shifting over a function by epsilon, by a small amount, as far as we know, this is not, the red thing is not a linear multiple. It's not a scalar multiple of the blue function. And so, as far as we know, if you have this function d to r, the linearity would say that if I double the original phi, or if I multiply it by 1 plus epsilon or something, it won't change, oops, sorry, u here. It won't change u of phi very much. But given this kind of change, how are u of phi and u of phi sub epsilon related? There's really no guarantee that they would be related in any way whatsoever, or certainly that they would be close to each other. And that's really what we want, right? Because remember, u are one of our models, one of our physical models, is that let's like a temperature distribution, and we'd like to be able to model idealized like points, sources of temperature, like hitting it with a soldering iron. And then phi was the thermometer, which had some sort of spread out response to that temperature. And this only really makes sense if similar thermometers. Let me see if I'm still here. If similar thermometers give similar results. Otherwise, we're really not modeling what I claimed we were modeling. And so far, everything I've said about distributions, there's nothing I've said that really models this idea. And so we could have had something where you put a thermometer with this temperature response profile in this location and it gives you a certain overall average temperature reading, and you move it a nanometer and it gives you a totally unrelated number. That's ludicrous. Okay, so we need to fix that. So there's a that's kind of a vague motivation, but powerful. And then there's a more specific motivation for why we need more, which is making sense of convolutions and seeing if convolutions are the nice objects. When we use Duhamel's principle, the result of that should be a nicer object than we know so far. Okay, so um, it's going to be a bit of a complicated story, but I hope not too complicated, and it's going to bring up a lot of great side issues. Okay, so there's a roadmap here. I realized in looking at this one more time before I started doing the videos that I was producing something that's kind of just structurally complicated. There's going to be two versions of convolution. Or actually, the first thing we're going to do is we're going to realize we could have defined convolution of a distribution and a function in a rather different looking way. And so I'm going to have a distribution convolve with a test function, the new definition versus the old definition that we've seen before. Okay, so the goal here is that eventually they really are secretly the same. So I'll give away that punchline. We don't actually want two different definitions of convolution, and we'll be able to use both of them in whatever circumstance we want, which is appropriate once we prove they're the same, but that'll take a while, definitely a few videos. Okay, so that's going to be one of the pieces of the structure. In proving that the new definition even makes sense and produces something decent, and that those are actually going to give the same answer, we're going to end up proving things about, or we're going to end up showing ourselves that exactly what we need to complete the definition of the distribution. Okay, so in that process, we're going to go through 4 possible conditions. These are continuity conditions that make precise the idea of similar thermometers give similar results. Possible has an L in it, and it's just going to be, I didn't come up with any clever names. They're all continuity conditions, so I can't call them anything but that. So conditions A through D. And D is going to be the final answer. We really will, in this handout, and so a few videos from now, we really actually we'll get the real definition of a distribution that we've been waiting for a while. Okay. So these ones, so A, B, and C, will be interesting and plausible in their own ways, and but they'll more or less fall by the wayside in favor of condition D as a definition of distribution. And we'll talk about, once we get all 4 of them on the board, we'll talk about the relationships and why, how D sort of supersedes all the other 3. Okay, and then another thing we're going to see is this is a great place where 2 super important concepts from analysis come through, and that's uniform convergence of a sequence of functions, or like a parameter, a family of functions parameterized by some like a time parameter, like for example, like this idea of taking a function and sliding it to the left or right by translation. Okay, and a related notion, although it's important not to confuse it, for a single function, a better kind of continuity of a single function, which is called uniform continuity. Fundamental concepts in analysis, and this was a great time to actually introduce them. And that's one of the things I want to do in these videos, is be motivated, as the title says, motivated to introduce these ideas of analysis. Okay, but I want to make clear these are ideas about ordinary functions and maybe sequences of functions. They don't directly have anything to do with distributions. They're just going to be really crucial for understanding these ideas of convolution and distributions. Okay, so a lot of long-windedness without any real problems. Okay, so here's the I won't do too much more on this intro video for this handout, but we've got this formal similarity, which I hope you've noticed, at least subconsciously, between a function acting as a distribution on another function, a test function specifically. I'm going to more or less consistently use t's and taw's through this whole video, but not for any particularly special reason, just because that's left over from the idea of like convolution and duhamel and things like that. You could think of it as x's, y's. Okay, so there's one of our core concepts, thinking of a function and thinking of it, promoting it to be a distribution, basically. And then there's the notion of a convolution, which is also defined by an integral. But this is a number, this is a function of t, and so you still take two functions, multiply them together, but you translate this guy, and then depending on how much you translate it, you say that's the value of this weighted moving average, the convolution at t. Okay, and of course, I'm going to freely, whenever I feel like it sets up a proof better, I'm going to freely change it to this if I want. Okay. So let's remember some notation. There's this notation of translation of a function. Oh, and see here I'm using x already. Doesn't really matter, it's a dummy variable. That g sub a is just the translate, just like I was using with phi a minute ago. Just translated by a. That's translated to the right if a is positive. That's why the minus sign. Okay. And there's some sort of mildly deep group theory issues there, by the way. Why that's a minus sign. And then g check, we've seen that a little bit, and this is just a terribly useful thing, is just flip it across the y-axis, flip the graph across the y-axis. Okay. And that lets us say that f star g of t, it lets us really emphasize the analogy here. Okay. And that's going to be, t looks really weird. It's going to be the integral. Okay, well, one of the things is I can switch this around. This is going to be f of, oh, sorry, this guy, f of tau g check of tau minus t. Oh, hey, that's g check sub t. Do I dare? Yes, I dare. Okay. Integral of f of tau times g check translated by t evaluated at tau. And that is exactly just f applied as a distribution to the flipped and translated version. I'm going to put a parenthesis here to emphasize it's the check, do the check first, and then translate it, because you could get a slightly wrong answer if you did it in the opposite order. Okay, so the convolution actually really can be created from this one concept. This is kind of the core concept. And then there's just translate or flip g, because everything works out, the signs and everything works out much nicer there. Flip g and then translate it by however much you want by t, and then let f act on it. That gives a number for every t, and that's of course the function f star g of t. Okay. So here's the deal though. Anytime we've analyzed some concept and we've seen that it can be expressed entirely for functions, for a function f. I haven't said anything about distributions, but anytime you have a concept that applies to a function, and that the only place that function has to come in is in this role where it acts as a distribution, we've now created a new definition for distributions. Okay, and that means this is an alternate definition of, I'm going to call it U star nu. Again, it's not going to be different, but it's going to take a while to prove that it's the same. U star nu G. Okay, so that's the convolution now of, and so this is the answer to number one. We're finally getting to the actual problems. This is a convolution of an arbitrary distribution with a test function. Still really important. It's going to be important that this is a test function, although right now I haven't really assumed that in any strong way. But I'm going to assume it's still a test function for now. In U star nu G, this is rather different from what we had before. We defined the convolution of a distribution and a function, a test function, to be a distribution. But now, this is really a big deal. I'm actually defining it as a pointwise function. And we're hoping it's not the world's most bizarre and ill-behaved pointwise function, but we actually do have a definition of the function. And it's exactly, it just says, take G, flip it, translate it by whatever this number T is that you're thinking of evaluating this guy at, and evaluate it at U. Okay, so that's a definition of the new style convolution of a distribution and a test function. Okay, now the question is this equal to the old one? Okay, I can't even say of t here though, because there wasn't a definition. I didn't have a definition that said this was a a pointwise function. Okay, so what we really want to say is, okay, I'm going to promote this to be a distribution by letting it act on some different test function. Oh, now that needs brackets. Test function phi. Is this equal to what I would get if I took the old definition of a distribution and acted on phi? And by definition, that's where this is another place where we needed that check notation. You're going to get it confused if that's still there. That was, we look at the convolution of test function with test function, which is totally well defined and beautiful, and then we let U act on that convolved test function. So are these guys equal? That's going to be a big question. And one of the ways, and just a little preview of the next video, well, I'll stop with this one in a second. Notice that comes back to that issue of similar thermometers give similar results. This is exactly taking a test function, like G, which happens to be checked, that's not a big deal, and sliding it over a little bit and comparing two values of U on that sucker. We don't yet have anything to say that they're related at all. As far as we know, I could, with a little bit of time, I could define a quote distribution for you, a linear function on test functions, that gave utterly random and unrelated results for every value of t. It would be the furthest from a continuous function you could ever imagine. And that's probably not what we want to have here, especially since every example we've seen of these guys, of distributions, has actually been really nice. Okay, so that's where we're going to go to next time.